Alrighty, good morning, lads and ladies. Welcome back to Pre-Calc. Today we are going to continue talking about exponentials and logarithms. Last time we saw what logarithms are and sort of where they come from, but we haven't gotten to play around with them very much. So today we're going to look a little bit deeper into the formal definition of a log and all of that good stuff. So just 1 second. There we go. Oh, let me flip on the document camera. We can get moving. So just to make sure I remember, because I have way too many of you guys in pre-calc right now in different classes in different places. On Tuesday, we finished up talking about exponentials and we introduced or motivated the log by talking about that equation 2 to the x equals 3. Is that right? But we have not yet formally defined the logarithm?
Yeah, that's correct.
Okay, very good. Then that's where we're going to pick up. That means we're moving into section 4.3 properly today. And I also want to talk to you a little bit about an extra assignment I'm going to have you guys do, something that is both statistically important for the department and I think many of you will benefit from. So first today, we're going to work with logarithms. But first, a little announcement. Something I noticed when I worked with my class on Wednesday with this material, talking about transformations and graphing other exponentials and other logarithms by like shifting exponentials and logarithms around, is that the transformation section from, what is it, 2.6 hasn't really sunk in all the way. A handful of you are quite good at it, and most of us have some grasp of it, but I think we all need a little bit more practice on it. Victoria, I'll address that in just 1 second. So before we go into the new material today, there's kind of 2 reasons for this. So I've identified a section where it feels like we need a little bit more practice. And I think everybody would enjoy having a few more points on that last test. But if the idea of a curve isn't something that sits well with me. So here's what we're going to do. The department previously, there's this thing we call the GELO. It's a general education learning outcome, and it's a statistic that we need to track for the course. It's something we hand up to the state. It has nothing to do with your grade, but it's a way that the state kind of measures how well this college is doing compared to other colleges when it comes to certain things that the state believes are important to track. One of those topics, so I get to choose the topic, one of those topics is transformations. And I think if I have to look through all of the GELO certified topics for one that our MAC1140 cohort most needs new practice with, it is this topic. I think it's something that is hugely important moving into calculus because it largely determines how well you can picture a graph right away. And that's something that you really want as calculus students. Now, because it's not, it's a new change. We used to get GELOs on the final exam, right? There would just be a few questions on the final exam. And if you got that question right, you would get the GELO for that. If you didn't get the question right, you wouldn't get the GELO for that. This semester, though, they're changing it. They want the GELOs to be done as worksheets, totally separate assignments, not on the final. And since I don't have a place in the syllabus for a worksheet grade like this, what I'm proposing is this. I am going to send you guys something like this. I think I'm going to rewrite it because these graphs are kind of ugly and I want it to look a little bit nicer than this. But I'm going to send you guys a worksheet like this. You have to complete the worksheet. It's not an optional thing, but completing the worksheet, I will give you some points on the last test, right? So kind of like extra credit on the test. You can think of it that way. I think there's 4 questions, and maybe we'll do 1 point per question, so you can earn like 4 points back on that last test, which is significant. That's like halfway from one letter grade to the next letter grade. It's not an extra credit assignment in the sense that it's optional, though. It is something you have to do. They just kind of sprung it on us, and we need some way to get the Jello. They said we can't do it on the final anymore. So they just said, you got to do this extra assignment. I know it's a bit of a pain in the ass, but it's like a little worksheet. And I don't think it'll take you more than 10 minutes. And everybody who does it and answers these questions correctly will get 1 point of extra credit, think of it like that, or 1 bonus point on their last exam score for each correct question. So you can see here what these are. They give you the graph of a function. And like I said, I'm gonna redo this because I'm really not happy with the quality of the worksheet they provided. The graph will be a little bit more clear on the actual worksheet I send you. They're going to give you the graph of a function f, and they're going to ask you for the transformations to get these 2 new functions. Then in question 2, you're going to graph both of the functions from part 1, f of x minus 2 and f of x minus 2 on this coordinate axis. Then in the third question, they ask you whether this is an even function, an odd function, or neither. And in question 4, they say totally different function. Suppose f of 4 is equal to 3, and some new function k of x is equal to 2 plus f of x plus 1. And they ask, since f of 4 is equal to 3, what point can you say for sure is on the graph of this new function? So I know this is a bit of a kind of coming out of nowhere thing, but the transformation section is a section we need more practice with, and it is just something that the state requires us to do. So as much as I don't like kind of the hiccup in the middle of things here, I am going to post this to Canvas. I will post an announcement reminding you guys that it needs to be done, and then you will submit it to an assignment on Canvas. And then I will go in and grade them, of course. And for every question you get correct here, I will give you 1 bonus point on that last midterm test. So you can earn up to 4 bonus points, bringing you from, a middle B to an A, or from a middle C to a B, and so on. All right, enough of that.
So, excuse me, from what you're saying, the average for the second test was not as good as the first one?
It's not terrible. It's not anything like that. Really, the reason I chose the transformation section here is because when I look back over the first test, and as I've been talking to my other students in other MAC1140 classes about how to graph these. So like your last 2 homeworks have had you graphing shifted exponentials, transformed exponentials. And today we're going to graph some shifted and transformed logarithms. Those seem to be the things that people are struggling with the most right now. So this was the topic. I had like 4 topics we could choose. This was the topic of the Jello assignment that I elected to go with. I see there's a question in chat here, but yeah, the average so far is not that bad. The average so far is right about where the last test's average was. There were some questions in chat that I want to address. So Victoria says, are we going to have a new homework today? Yes, we are going to have a new homework today. I know that last homework has 45 questions, but most of those go very, very quickly. So the vast majority of those questions are things that after we've talked today a little bit, I think you'll find very simple. The new homework set will be much shorter, but it will have a little bit more graphing and domain type stuff about logarithms. So don't feel intimidated. Remember the homework that I opened on Tuesday, that's not due today. I gave you guys a full week on that just because I knew it's a longer assignment. But once you get in there and start grinding through it, I think you'll find that it goes very quickly. And then Christopher asks, due date for the Jello assignment. So I haven't set one yet. I'm going to have to think about that a little bit. I do want to make sure you guys have enough time to do it without falling behind on your homework, probably like a week or something like that. So I'll post it up today if I have time, and then it'll be due sometime at the end of next week or the beginning of the week after. It's not a time sensitive thing really. I just need you guys to get it done within a couple of weeks, because again, it's not something that's like super important for the class. It's something that's more important like statistically for the state. So the Jello assignment on transformations is a required bonus assignment. It will be posted like I said, I want to rewrite the thing because those graphs are so ugly, but it will be posted this week. due week after next. Yeah, as soon as I can get them. So I have a bunch of people who are taking makeup tests. Those are coming in on Friday, and I don't like releasing all of the comments until after that's been done. So the soonest I'll start releasing the graded versions of the test will be Friday. About half of them are graded. So far, the scores are not that bad, but I need to wait until everybody's taken the test before I can actually publish the comments. Alrighty, what else do we need to say here under the thing? So everybody's clear on what this assignment is. It's just going to be a little worksheet that I will post to Canvas for you. Although it is a bonus assignment, meaning it's not, you wouldn't lose points for not doing it, it is required. So I need you guys to do this, and it will earn you some bonus points on your midterm score, up to 4 of them. 1 bonus point for each question that's answered correctly. I'll set the due date to be like a week and a half past, at least a week and a half past when we open the thing, to make sure you guys can do it in your own time. That's it. All right. So let's get into logarithms. No, sorry. So another question coming in chat. Was that last test worth more than the previous test? Nope, same amount, 100 points. So all the midterms are worth 100 points. Okay. So last time we saw the equation 2 to the x equals 3. And observed that its solution, which was like x is about 5849-ish, comes from the inverse of f of x equals 2 to the x. Today, I want to talk in detail about that inverse function. So, definition. The inverse of the function of the base a exponential f of x equals a to the x is called the base a logarithm, and the notation is log with a little subscript a. So that is the name of the function. And then the input variable goes over here of x. No, Victoria. So this in Canvas right now, none of the free response stuff is in. So yeah, all of those still need to be entered. So none of the grades that are displaying in Canvas right now are the final grades. Okay. So this equation, reasonable looking equation, we saw it had a solution by thinking about the graph of 2 to the x and seeing where that intersected with the line y equals 3. That solution was somewhere around 1.5, and we were able to calculate it to a few decimal places using some mysterious technique that I haven't shared with you yet. I claim that that solution comes from the inverse of the function 2 to the x. So in order to start exploring things like this in greater depth, I want to give the inverse to this function a name. Right, so a to the x in general instead of just 2 to the x. We want to look at the inverses of all of those exponentials. It turns out there's no nice algebra formula for these things. There just isn't. Like in terms of square roots or powers or dividing by variables, rational functions, there's no nice way to write down the inverse to an exponential function. So what we do is we just call the thing a logarithm. We say, this is definitely a one-to-one function. The graph of all these exponentials pass the horizontal line test. So they have to have an inverse, whether I can find a formula for it or not. So let me just give the thing a name. Let me call it the base A logarithm. And I'll say, all right, the inverse to that a to the x function is the base A logarithm of x, some new function. And all we know about it is that it's the inverse of this exponential. This has a few immediate consequences. All right, and you can think of these as alternate characterizations of the logarithm. We know, so first, we know that if you take a function f and you plug that original function into the inverse, so you take f inverse of f of x, what does this always simplify to for any function f?
X.
Yeah, that should always simplify to x. And if you compose in the other order, you take f of f inverse of x, what should that always simplify to? Don't overthink it.
Would it be x?
Also x, right? Remember, the inverse is the function that exactly undoes the original. So if you take some number x, do the original function to it, then do the inverse to that, these guys undo each other. So you just get back whatever you started with, which is x. And the same thing's true in the other order. If you take some number and you do the inverse function to that number, then you do f to that thing, again, these guys exactly undo one another. So you should get out precisely what you started with. So if I write down this statement for these functions, which are inverses of each other, what do I get? Well, f inverse of x is the base A logarithm of x, or log sub A of x. So f inverse of f of x is the log sub A of A to the x. So this is this for these functions. I'm just taking this thing and plugging this thing into it. And because they are inverses, this will always simplify to x. And if we compose the other way, if I take this thing, the original function f, and I plug this thing in for x, then that should also simplify to x. So this means that a raised to the log base A of x should also always simplify to x. And for many people, this is just where they stop. They say, this is the definition of the logarithm, and this is the kind of best way to interpret it, and they make you work everything out from there. One of the places I actually really like your textbook is in this section, because they give one more characterization, one more immediate consequence. Really, this is the way we like to think about logarithms and exponentials interacting when we go to solve equations like this. But early on, when you're just trying to figure out what is the base 4 log of 25 or something, when you're just trying to find the outputs from a logarithm, when you're just first starting to get to know the function, we can say that the logarithm is characterized by this relationship, that the base a log of x is equal to y, means that a to the y is equal to x. And if you think about it, these really do say the same thing. And this second box has an interpretation in terms of words that I think you'll find very useful. This says that the base a log of x equals the number to which you must raise. So think about it here. The base a log of x is equal to y. So y is this thing, means a to the y, a to this thing is equal to x, right? And that's exactly what we say here, right? A to the y, the base a log of x is equal to x. But thinking about it like this allows us to more easily get to this orange interpretation, which in plain English says that the base a log of x is the number to which you must raise a in order to get x. So if I ask you, and I'm going to do this in just a second, what is the base 10 log of 100, for example, you would say, oh, okay, well, the base 10 log of 100 is the number to which you must raise 10 in order to get 100. And that's a mental problem that we can work out in that language. And this is how we're going to first get to know logarithms. I want to take a quick second to make sure everybody has this stuff down in their notes nice and clear, because you're going to be referring back to all three of these statements readily, often, regularly, frequently. Okay. Before we get to straight up evaluating logarithms, let's rewrite each logarithm statement as an exponential statement. So first, we'll say that the base 10 log of 100,000 is equal to 5. So there's nothing to solve here. I just want to rewrite this true statement about logs as a true statement about exponentials. And I'll give you a few others, like the base 2 log of 8 is 3. The base 3 log of 1/9 is -2. And the base pi log of 1 is 0. All right. So I want you to take a look at that blue box statement from the previous page that had the word means in it, and tell me what this means. What does it mean to say that the base 10 log of 100,000 is equal to 5?
Would it mean that 10 raised to 5 equals 100,000?
Perfect. Did everybody hear that? That was beautiful. Thank you, Megan. This means 10 to the 5 is 100,000. right? The base a log of x equals y means a to the y equals x. And it's a new way of thinking. So we're going to start off very gentle, but we're going to build up quite quickly. So I want you guys to really think along with me with these next three, okay? I want to hear from some of my quiet folks today. What does it mean to say that the base 2 log of 8 is 3? What is the equivalent true statement about powers?
2 to the power of 3 equals 8.
Perfect. This means 2 to the 3 equals 8. All right. The next one might not be super obvious, but if you follow the same pattern, you'll arrive at the correct conclusion. So what does it mean to say that the base 3 log of 1/9 is equal to -2?
Would it be 3 to the power of -2 equals 1/9?
Perfect. 3 to the -2 equals 1/9. And if we think about this, this is also a true statement, right? 3 to the -2 is the reciprocal of 3 squared. So 1 over 3 squared. Well, what is 3 squared? It's 9. So yeah, 3 to the -2 is 1/9. All right, this last one's kind of fun. What does it mean to say that the base pi log of 1 is equal to 0?
It would be that pi raised to the 0 equals 1, because anything raised to the 0 equals 1.
That's exactly correct. Pi to the 0 is equal to 1. And a fun observation about this last guy, the first three, these statements are very sensitive to the base, right? If this base here wasn't a 10, then this wouldn't be true, right? Like 7 to the 5 is definitely not 100,000. Only 10 to the 5 is. 2 to the 3 is 8, but like 4 to the 3 sure as shit is not. The last one, though, this is true no matter what base you're using. Pi to the 0 is 1, 10 to the 0 is 1, 3 to the 0 is 1. So you could change this pi to anything you want. The base a log of 1 is always 0, no matter what you're using for a. And that's a fun fact that we'll write down a little later when we discuss properties. Okay. Let's evaluate some logarithms now. Now that we know how to reinterpret them as statements about exponentials, you're going to do this part in your head, and you're going to come up with this number for me. So first, let's evaluate the base 10 log of 1,000. I'm going to write a few others down here. We're also going to evaluate the base 2 log of 32. The base 10 log of 0.1. And the base 16 log of 4. Okay. So I want to know, what is the base 10 log of 1,000? Whatever this is, it should be the power to which you raise 10 in order to get 1,000. So to what? Yeah, exactly. It's 3. Thank you, Jimmy. Yeah. The base 10 log of 1,000 is 3 because 10 to the 3 equals 1,000. Now, you don't always need to write the because. Yeah, I'm just writing it to help you see it if it's not jumping out at you, because I know we're all going to get this at different speeds, and that's fine. But this is the reason why. So when we ask ourselves, what is the base 10 log of 1,000? We're asking, to what power must I raise 10 in order to get 1,000? To what power must I raise the base in order to get the inside? And it's not multiplication. It's not anything to do with roots. It's its own new operation. So you really do have to think about it. All right. What is the base 2 log of 32?
Would it be 5?
Exactly, yeah, this is 5, because 2 to the 5 is 32. So base 2 log of 32 is 5, because 2 to the 5 is equal to 32. All right, this one's a little tricky. Base 10 log of 0.1.
Would it be
-1?
-1?
Yeah, it's -1. So I would even first write this as the base 10 log of 1/10. I think that's easier to see, right? 0.1 is the same as 1 over 10. And 1 over 10 we know is the negative first power of 10. So the base 10 log of 1/10 is the power to which you raise 10 in order to get 1/10, and that is -1. I'm not going to write the because statement for this guy. Okay, what about this last one? To what power must I raise 16 in order to get 4? Now maybe I will go ahead and, so while you're thinking about it, I'll write this, because 10 to the -1
Would it be 1/4?
is 0.1. You're thinking in the right direction with 1/4, but that's not quite it. So 16 times 1/4 would be 4, but we want to know 16 raised to what power is 1/4. Or sorry, 16 raised to what power is 4?
1/2.
Very good. Yeah, 1/2, right? The square root of 16 is 4. This is 1/2, because 16 to the 1/2 is the square root of 16, which is 4. We starting to feel a little comfy with these? In a minute, we're going to look at some graphs. We're going to talk about domains and ranges and asymptotes, all that stuff. So we really need to be super duper comfortable with these basic statements before we go there. Any questions about any one of these parts here from these last two examples? Don't be shy. If you got them, this is the perfect time to ask. All right, you have plenty of questions of both of these types in your homework to practice, both rewriting log statements as exponentials, rewriting exponentials as logs, and evaluating logs. I want to share with you some statements about logarithms that are always true. We call them properties. And when I don't want to write or say the full word logarithms, I will just say log, right? So logs means logarithms. Okay. The first one here is that the base a log of 1 will always be 0, no matter what your base is. Right? This is because any number to the 0 is 1. At least any number that could be the base of a logarithm. Remember, a in the base of the logarithm is the base of an exponential, and those bases always have to be positive. The second property here, kind of in the same vein, is that the base a log of a, this will always be 1. Same sort of logic, right? Any number raised to the 1 is itself. So to what power must you raise a in order to get a? You must raise a to the first power. To what power must you raise a to get 1? Always the 0 power. The last two here, your book lists them again, is that the base a log of a to some stuff, whatever that stuff is, will always be that stuff. And we can go the other way a raised to the base a log of some stuff, whatever that stuff is, will always just be that stuff. Right, so the base a log of a to your mom is your mom. I do want to make a little note here. The base a is always positive. Because it's the base of an exponential, right? And we talked about that last time. The base of an exponential always needs to be positive, lest we have lots and lots of imaginary numbers and weird stuff going on with the graph. Because this base here, a, is the base of the exponential for which this is the inverse function, the base of a logarithm is always going to be positive. We'll never work with a negative base. All right, some silly examples. We can calculate the base 5 log of 1, the base 5 log of 5, the base pi log of pi to the e. All right, what's the base 5 log of 1? No calculator involved here, just what is this?
0.
Definitely 0, right? Base a log of 1 is always 0 for any base. What's the base 5 log of 5?
1.
1, because 5 to the 1 is 5. All right, how about this guy? What is the base pi log of pi to the e? What about property 3?
Would that be E?
It is. It is. And having used the symbol E for the first time today, I want to introduce some special notation. You remember we said on Tuesday that there's really only one exponential function anybody cares about. It's e to the x, right? All of the exponentials are kind of the same, and there's only one that anybody really gives a shit about. The same is true for logarithms. I'll put it, and we'll do it down here. So we have a special notation for kind of the two most common bases. Base 10 logarithms used to show up a lot more than they do now, back in the era of like working with slide rules, because powers of 10 are important in our number system. Our number system is the decimal number system. It's a base 10 number system. The logarithm with the base 10 is usually just written without any base. And if you look on your calculator, you probably have a button that just says log. That is the base 10 logarithm. And this is called the common log. The other one that is special here is the base e logarithm. And this is the one that everybody actually uses. The base e logarithm is usually just written as ln. So the log base e of x is just the ln of x. And this is called the natural log. Just like e to the x is called the natural exponential, the base e logarithm is called the natural log. Okay. So I want to look at some graphs. We did quickly sketch the graph of the base 2 logarithm the other day. I am going to sketch that graph again, and then we will graph some functions as transformations of that guy. say use the graph of y equals log sub 2 of x to sketch f of x equals, let's do log sub 2 of negative x and g of x equals log sub 2 of x plus 1. So first I'll give you the graph of the base 2 log. We had it the other day, but I'll go ahead and remind you what that looks like. We're going to talk about the domain and the range. So this is y equals log sub 2 of x. And I'll mark this here as 1, and this here as 2. And we have 1, 2, 3, 4. Points on the graph of the base 2 logarithm came from points on the graph of 2 to the x, just flipped over. So like 0, 1 is on 2 to the x. So 1, 0 is on the graph of the base 2 log. 1, 2 is on the graph of 2 to the x. So 2, 1 is on the graph of the base 2 logarithm. And 2, 4 is on the graph of 2 to the x. So 4, 2 is on the graph of the base 2 logarithm. There's more though. If this is -1, then this right here would be the point 1/2, -1, because the base 2 log of 1/2 is -1. And we could even say, if this is -2, then this is the point 1/4, -2. So let me label these. These are kind of tricky ones. Okay. And the horizontal asymptote for the exponential becomes a vertical asymptote for the logarithm. And what this graph looks like, and you need to remember this forever and ever, amen. This is a new one of your parent functions. Looks like this. All right. This is the graph of the base 2 logarithm, and all the other logarithms look the same. Right? They have different specific points in the same way that those exponentials all look the same but have different specific points. In particular, the domain here, I know we said this on Tuesday, but I want to make sure we've got it clear. The domain of the logarithm is the range of the exponential. It's 0 to infinity. And the range here is the domain of the exponential, which was -infinity to infinity. So this goes all the way down, right? This little guy at this vertical asymptote, he's blowing up all the way down to -infinity. I think that's pretty clear from the picture. What's not super obvious from the picture is that this goes up all the way to +infinity. It takes its time getting there, right? It's like growing pretty slowly, but there is no horizontal asymptote here. This thing goes all the way up. And I'll warn you, if you get used to graphing these things on graphing calculators, it's easy to misunderstand what's going on here. A lot of people have this misconception that the graph of the logarithm starts at this point, but it does not. The graph of the logarithm goes all the way down here. All right. Yeah, if you want a table of values for this, we can. So here's x, and here's the base 2 log of x. I'll put the x's in increasing order, and I'll put the ones on here that we use, and maybe 1 or 2 more. So at 1/8, this would be -3. At 1/4, this is -2. At 1/2, this is -1. At 1, we have 0. At 2, we have 1. At 4, we have 2. And the next obvious guy would be 8, 3. Well, we're not thinking of these as coming from tables, right? So I can give a table if you want one, but remember, we're thinking of these as just coming from the definition of the logarithm as the inverse of the exponential. So we're thinking about the points on the graph of the exponential and then flipping those points over to get points on the graph of the log. But if you want to know what sort of numbers are nice to plug into the base 2 logarithm, they're going to be powers of 2, right? Think about the examples where we've evaluated logarithms so far. All of the numbers that we were plugging into the log in those examples were powers of the base. So like 1/8, that's 2 to the negative 3. And that's why this is negative 3. 1/4 is 2 to the negative 2. 1/2 is 2 to the negative 1. 1 is 2 to the 0. 2 is 2 to the 1. 4 is 2 to the 2. And 8 is 2 to the 3. So the numbers in general that are nice to plug into the base A logarithm, the numbers you can plug in there to get nice numbers out, are powers of that base. Could be a positive power or a negative power, but powers of that base. And that kind of addresses a question that came in the chat earlier also. So Megan, is there a nice way to figure out the output from a logarithm? You have to think of the input as a power of the base. And if the input is not a nice power of the base, then there isn't a clean way to figure those out. We'll talk about that a little later. There are some tricks. I will show you tricks to doing this, but for now, we're just wanting to wrap our heads around the basics. Okay, so here's the original graph. Here's our table if you want it. Make sure you remember the domain and the range here. In particular, you cannot take the log of 0. Can't plug 0 in, right? This vertical asymptote, this function is undefined at 0. And you cannot take the log of a negative number, right? There is no such thing as the base 2 log of negative 5. Doesn't exist. Negative 5 is not in the domain. Okay, so I want to sketch f of x, which is the base 2 log of negative x. And to do this, this comes from what transformation? What transformation do I need to apply to the original function to get this guy with a negative on the inside?
Does it flip over the x-axis?
Very good. This comes from reflecting y equals log base 2 of x horizontally, i.e. over. Oh, did you say x-axis? I'm sorry. No. This is going to be a horizontal reflection, a reflection over the y-axis. I'm sorry. So when you multiply on the inside by a negative, that flips things over horizontally. And a horizontal reflection is a reflection over the y-axis here.
Excuse me, I have a question.
Yeah.
If the negative is on the outside, does that mean it reflects over the origin?
Not quite. A negative on the outside would mean a reflection over the x-axis.
Okay.
So yeah, multiplying by a negative on the inside flips you over horizontally, flips you over the y-axis, i.e. kind of flips your domain around. And a negative on the outside flips you vertically, flips you over the x-axis, flips your range around. If you're to do both of those, having a negative on the outside and a negative on the inside, that would be both a vertical and horizontal flip, and that is a reflection through the origin. So maybe that's what you're asking, right? If you also had a negative on the outside, then that would put you like reflected through the origin.
Yeah. Thank you.
Cool. All right. So this first guy I want to graph comes from taking the graph above and flipping everything over the y-axis. What that means is we can sketch the shape of this thing right away. We don't have to plot points or anything. We will plot some points, but we can say right away what this looks like. It looks like this. All right, I take this guy and I flip him over like that, and I get this guy. The vertical asymptote doesn't move. It's still the line x equals 0. That point 1, comma 0, when he gets flipped over here, he becomes -1, 0. That point 1/2, comma -1 becomes -1/2, comma -1. That point 1/4, comma -2 becomes -1/4, comma -2. 2, comma 1 becomes -2, comma 1. And I've got room for it just barely here. 4, comma 2 becomes -4, comma 2. This is y equals log base 2 of -x. And this is the x-axis. So I just pick that whole graph up and I flip it over the y-axis. And I get this. Right, and of course this goes, I don't have a lot of room here, but this goes on and on like that, just as the one above did. I'll do part B on a separate sheet of paper so we have plenty of space. Before I do that, what's the domain of this new function?
-infinity 0.
Very good, -infinity to 0. All right, now I have nothing over here. Everything is over here, where all the x values are negative. We don't include 0 because I have a vertical asymptote there. This function is undefined at 0. What is the range? When I flip this over horizontally, does that do anything to the range?
It would stay the same.
Yeah, it stays the same. Still -infinity to infinity. I haven't done any sort of vertical stuff. All right, the only changes here are horizontal things that affect the domain. Okay, let's try the other one. I'll keep this black graph where we can see it. And now I want to sketch g of x, which is the base 2 log of x plus 1. What's the transformation here? This comes from doing what to the original function?
You move it over 1.
Yeah, so by
So
over we
to the
mean
left.
horizontally, right? And is it going to be left or right?
To the left.
Good, we move everything to the left by 1. Comes from shifting y equals log 2x left by 1 unit. All right, so what's that going to look like? The first thing I would notice here is that if I'm going to pick this black graph up and drag everything to the left by 1 unit, this asymptote is going to move. It was x equals 0. When I move that to the left by 1 unit, that new vertical asymptote is x equals -1. You can always find vertical asymptotes of logarithms by setting the inside equal to 0. So the original has a vertical asymptote when x is equal to 0. It's because it's the log base 2 of x. This guy will have a vertical asymptote of x equals -1 because it's the log base 2 of x plus 1. So x plus 1 is equal to 0 when x is -1. So I have my vertical asymptote here. You approach it like this because we're just shifting everything to the left 1 unit. The point 1, comma 0, if I shift that left 1, becomes 0, comma 0. The point 2, comma 1, if I shift that left one, becomes 1, comma 1. The point 4, comma 2, if I shift that left one, becomes 3, comma 2. Right, and here's my graph. And we can track what happens to those other points also, but their coordinates are a little bit harder to sort out. So what do I get if I take 1/2, comma -1, and I shift it to the left by 1 unit? What is this point going to be?
Would it be -1/2?
Yeah, exactly. We're shifting to the left one. That means we're subtracting 1 from the x values. Positive 1/2 minus 1 is -1/2. So that's -1/2, comma -1. And what about the point 1/4, comma -2? Where does he go? If I take this guy to the left by 1 unit, where does he go?
-3/4.
Very good, -3/4, right? Again, we're subtracting 1 from the x value. So 1/4 minus 1 is -3/4. This is -3/4, comma -2. This is the x-axis, of course, and this is the graph. Y equals log base 2 of x plus 1. All right. So the questions in that 45 question homework set that's already up for you guys doesn't have any graphing of logarithms in it. It's all just like evaluating and restating logarithms as exponential, stuff like that. The new one that I'm going to put up for you, which I promise will be short, is going to be stuff like this: sketching transformations of logarithms, stating the new domain and the new range. So what is my new domain here?
-1 to infinity.
It's perfect. -1 to infinity. And just like we don't include 0 in the original domain, we don't include -1 here. This thing has an asymptote, a vertical asymptote, -1. What is the range of this new function?
-infinity to infinity.
Very good. Has not changed. Still -infinity to infinity. All I did is shift it to the left. Didn't do any vertical stuff, so couldn't possibly change the range. All right. So there's going to be plenty of this in your homework where you're going to practice sketching transformations and just looking at graphs of logarithms. It's important that you practice this for all the obvious reasons. In the future, especially in your calculus class, you'll be doing things with these functions, which will be very, very easy if you can picture the graph, but very, very hard if you cannot. And we really don't want to have to go through and make a table every time you want to graph some new function. You want to just be able to say, oh, I know that graph. I know what that looks like. So this answer makes sense. Or I know that graph. So this answer doesn't make sense. Really quickly, I want to restate some of the things we said earlier in terms of the natural log. So just like everybody loves the natural exponential, everybody loves the natural log. It's really the only logarithm that people in my field of mathematics ever mess with, and in most fields of mathematics. So I'll say recall. Graph y equals e to the x looks like this. Looks like any other growing exponential. The horizontal asymptote is y equals 0. I'll mark -1, 0, 1, and 2. So this point right here would be -1, comma 1 over e. This point right here is 0, comma 1. This point right here is 1, comma e. And the point above 2 here is 2 comma e squared. And remember what we said. We really want to just leave powers of e as powers of e. There's no sense in writing these things as decimals. They're not nice. Thinking about them as just powers of e is the way to go. But if you need to picture in your head about how big is e squared, just think e is a little bit smaller than 3. So e squared should be a little bit smaller than 9. So the scale here, this would be like 9-ish, a little smaller than 9. This is 1. This is a little smaller than 3. Similarly, 1 over e, pretty close to 1/3, right? Because e is pretty close to 3. So y equals ln of x looks like what? Well, it's going to look like all the other logarithms, but the specific points that we need to know are going to be a bit different. 0, 1 is on the graph of e to the x, so 1, 0 is on the graph of ln x. The next sort of obvious point on the natural logarithm comes from this guy. 1, e is on the graph of e to the x, so e, 1, and we just leave it as e. E, 1 is on the graph of ln x. And the next guy would be e squared. If that's e, that's like 3. E squared would be like way out here. That would be e squared, 2. Other points here, 1 over e, -1 would be on this graph. That horizontal asymptote for e to the x becomes a vertical asymptote for the natural log. And the graph looks like this. There we go. Like that. Oh. So this is e, 1. This is e squared, 2. All right. So this part of the graph here is coming from this part of the graph here. This part of the graph here is coming from this part of the graph here. We're just taking the original graph and flipping it over the line y equals x. Well, so yeah, the natural log is the inverse of the natural exponential, right? So ln of x is exactly the inverse of e to the x, in the sense that we use the word inverse for functions, right? It's not the reciprocal. It's not 1 over e to the x. It's the function that when you plug it into e to the x, cancels. And that's the next thing I wanted to say. So one of those properties of the natural log, we've really already said this, we're just restating it in the new notation. The ln of x is equal to y means that e to the y is equal to x. And all those other things that we said, like this was our characterization. Literally says the same thing we said on that first page. And then you also have these other statements like the ln of 1 is 0. The ln of e is 1. The ln of e to some stuff will always just be that stuff. And e raised to the ln of some stuff is also just that stuff. Okay. The domain of the natural log is the same as the domain of the other logs we've talked about. 0 to infinity, and the range of the natural log is negative infinity to positive infinity. Okay. I think it wouldn't be a bad idea for us to play a little bit with evaluating natural logs, again, just practicing the notation really. And then I want to do one problem where you find the domain of a logarithm function using algebra, rather than looking at the graph. You may have already found the ln button on your calculator, and you may have found the E button on your calculator. But I want to emphasize that with this problem, and with all of the problems in your homework set this week, except for the last couple, which say use a calculator, every other problem, unless it tells you to use a calculator, you should not use a calculator. We want to make sure that you understand how to do this stuff without a calculator. In the next class, Calc 1, we take the calculator away. So can we find the ln of e to the 8? Can we find the ln of 1 over e squared? And then I'll go ahead and say, can we find the ln of, let's say, these things get a little bit boring, don't they? E to the negative. All right. What is the ln of e to the 8? Remember, the ln is just the base e logarithms. It's the same thing as log sub e of e to the 8.
Would it be 8?
Mm-hmm. Yeah, exactly. This is 8. Okay, what about the ln of 1 over e squared? Think like that log base 3 of 1/9. Same sort of thing, right? This is the log base e of 1 over e squared.
1/2.
Almost. In fact, let me add, inspired by your answer there, to add one more. How about the ln of the cube root of e? We'll do that last. So for part B here, kind of the trick is going to be to rewrite this inside as a power of e. So if I rewrite the inside there as e to the negative 2, making sure to keep everything else the same, can we see what this is now? What is the ln of e to the negative 2?
-2.
Yeah. And it'd be useful to, let's see, where can I sneak these in here? Over here. So the ln of e to some stuff will always just be that stuff. So this is -2. All right, what about the natural log of e to the negative pi?
Still be negative pi.
This has to be negative pi. And then the last one, the natural log of the cube root of e.
3/2. Sorry.
1/3.
Yeah, this is going to be 1/3 because the cube root of e is e to the 1/3. That's one of those properties of exponents we talked about last week. And the ln of e to the 1/3 has to be 1/3 by this property here. Okay. So remember, ln is just a shorthand for log base e. So all the same rules apply. We just write it as ln to save a little bit of time. My last little note for you. We have now a new domain red flag. So remember, we talked about domain red flags at the start of the term when you're trying to find domains algebraically. And that is variables inside a logarithm. Because the domain of all of these logarithms is just 0 to infinity, just positive numbers. So if you have a more complicated logarithm expression and you want to find the domain, you need to make sure that the inside of the logarithm is strictly greater than 0. This gives me a quick opportunity to say something. One common misconception is that this statement, for example, is multiplication. This is not the natural log times e to the 8. The natural log is a function like f or g. This is the ln of e to the 8. So don't confuse this with multiplication. This is the function, and this is the inside of that function, like f of e to the 8. So when you're trying to find the domain of a logarithm function where the inside has some variables in it, you need to be mindful of this new red flag. So I could say find the domain of f of x equals the ln of 2x plus 1. And the red flag here is that I have variables inside the logarithm. So what we need to do is make sure that the inside is strictly greater than 0. That will give you your domain. Remember, you cannot take the natural log or any log of a negative number. If the inside here, 2x plus 1, were negative or even 0, then this whole thing is going to be undefined. So to find the domain, we need to solve the inequality 2x plus 1 is strictly greater than 0. And thankfully, this is a linear inequality. This is easy enough to solve. We can subtract 1. We get 2x is greater than -1. And then we can divide both sides by 2, and we get x is greater than -1/2. And that's your domain, i.e., the domain would be the interval -1/2 to infinity. All of the x's which are bigger than -1/2. And these can get a little bit more complicated if the resulting inequality is nonlinear. So we can find ourselves solving rational and polynomial inequalities if the inside of my logarithm is rational or polynomial. So if I want to find the domain of ln, or sorry, log base 2 of 4 minus x squared, the only red flag that's present here anywhere is coming from this variable stuff, which is inside the logarithm. So here we need to solve the inequality 4 minus x squared is greater than 0. Anybody remember how to do this? This is the sort of thing that we were just working on.
Would you write it in a reverse order and take out -1?
Oh, you could. You could write it as the negative of x squared minus 4 is greater than 0. But I don't think that's going to be super duper helpful. It wouldn't be wrong. And you could certainly solve it from there if you wanted to. But do you remember our procedure? So let's first say, how would you classify this inequality? What kind of inequality is this? Is it linear, rational, polynomial?
Polynomial?
Yeah, it's a polynomial inequality, right? So we want to pull everything to one side, have a common denominator if necessary, it's not necessary, and then factor everything, right? So everything's already been pulled to one side. There's no denominators to make common. So my next step would be to factor everything. And that will let me find those cut points. 4 minus x squared factors as 2 minus x times 2 plus x. And if you elected to factor out a -1 first, you would have negative x minus 2 times x plus 2, and you get the same thing. Now that I have everything on one side factored, I make a number line. I have -2 from this factor and +2 from this factor. That splits the real line up into several regions. And we've got lots of options. We could test a point. We could use end behavior. We could do all sorts of stuff. In here, let's imagine that I just test x equals 0. So if I plug 0 in for x to any of these forms of the inequality, here I'll get 4 minus 0 squared is greater than 0. This thing is positive, right? 4 minus 0 is positive. And then by multiplicities, each of these is a multiplicity 1 factor will be negative out here and negative out here. You could also get the negatives on the outer pieces here by thinking about the end behavior for this polynomial. This is an even degree polynomial with a negative lead coefficient, so it goes down on both sides. All right, so what is the domain of this function? The domain is the solution to the inequality 4 minus x squared is greater than 0, which is
-2, 2.
very good. And it's
With parentheses.
Yeah, very good. Open interval, perfect. Parentheses, -2 to 2, because both -2 and +2 make this thing equal to 0, and 0 is not bigger than 0. I could combine this stuff with other domain things, like if we had this whole thing divided by x, we'd need to make sure that the downstairs of the fraction isn't 0. If I put the whole thing under a square root, we would need to make sure that the inside of the square root is greater than or equal to 0. So this is just a new red flag. You add this onto your list of existing red flags, and we can take combinations of functions that include logarithms now and find their domain. All right, that's where I'm going to leave it for today. There will be another small homework set, just a very, very small one with a few graphing and domain problems, but I promise not a lot. I don't want to overwhelm you. Do make sure you're working on the homework set that we released on Tuesday, and please do that one first, right? We want to make sure that you're comfortable with the definition of the logarithms and just what they are before we do anything too crazy. Also, be on the lookout for that Jello worksheet. I will post an announcement to Canvas as soon as I finish rewriting it. I'm really not happy with the product that they gave us to give to you, so I want to give you something a little nicer. And remember that while that is, it's kind of a bonus assignment, it's just to give you some extra credit points on your exam. It is necessary. I need those stats to pass on to the state. Without them, I get in trouble. So if nothing else, think of it as a bonus for you or a favor to me, however you want to think about it. And you'll have about 2 weeks to get that done. Just a little review of transformations. Alrighty, gang, that's it for me for today. Work hard on that homework stuff. If you have any questions, anything you want to talk to me about, of course, you can come to office hours Monday, Wednesday, Friday, 1 to 2. Send me a Canvas message or an email or post to the Discord. I'll see you all next time.